Okay, so we had already talked about this MDP. We had already talked about this game and the way we were changing, right? What we said is we don't know transition probabilities, we don't know rewards. Laptop. Thank you. Chalo. So if everything is given to you, you can do offline computations and come up with the optimal answer. Okay? If you start playing, that is, you don't know what is the reward, you don't know what are the probabilities, then you don't have any choice but to play. Chalo. If transition probabilities are not given to us, if rewards are not given to us, what can we do? So we have no choice but you have to take actions, you have to see out there. So all we have to do is you have to go play it on your own and see what's actually happening, right? हमको पहले से we can't do anything beforehand. Okay? So we had talked about this. So if probabilities are not given to us, right, we don't. Now in this case only probabilities are not given to us, but what if even rewards are not given to us? Okay. So whatever we did just before, whatever they did, where you had to play, no disturbances by
सर अगर ट्रांजिशन प्रोबेबिलिटी और रिवॉर्ड्स दोनों नहीं है तो अपन एक्शंस ले लेके फिर पता आगे पता करेंगे और ये रिइंफोर्समेंट करनी पड़ेगी.
See, no. Normal thing is, so the way it happens today, if you can solve an MDP and all the information required to solve that MDP is beforehand known to you, okay, then that's not reinforcement learning. Okay, if you have all the information required for planning, so if you don't have all the information required to solve MDPs in this particular case, then that's not reinforcement learning. Basically any kind of learning, because in that case you are not learning anything, actually everything is given to you, right? So you can plan but not learn the way we understand learning. But if something is not given to you and you are still supposed to solve that same thing, then you are supposed to extract those values by taking actions on your own, right? So in this case, हो सकता है probabilities are not given to you, transition probabilities, it is possible both T and R are not given to you, right? I mean, you can go and make things as generalized as you can. You say कि I don't even know what are the total number of states. I don't even know what action is possible in every state. So all those kind of things are possible and they only make our life more difficult, right? So if somebody comes and tells us कि the only unknown that you have is, the only thing that you don't know is, let's say, just these probabilities, fine, you need to go and learn them. So that kind of learning is what we call reinforcement learning. Or, but here rewards are actually given to you. In general, even they may not be given. In general, you may not even know कि states कितनी है, कौन सी, so कौन सी state में क्या action available है. You can make it as generalized as you can. Okay? What happened? Right? So that wasn't planning, it was learning, what we did just in last game. Specifically reinforcement learning. So there was an MDP, but you couldn't solve it just with computation. We had to take more steps. You needed to actually act to figure it out. Important ideas in reinforcement learning that came up: exploration. We'll see what exactly exploration is. So you have to try unknown actions to get information. Exploitation, eventually you have to use what you know. Regret, even if you learn intelligently, you make mistakes. Sampling, because of chance, you have to try things repeatedly. Difficulty, learning can be much harder than solving a known MDP, because it involves solving a MDP plus learning those values. Okay? So, exploration, you have to try unknown actions to get information. Exploitation, this is a very big trade-off in reinforcement learning. So, what is exploration?
Exploring different possibilities.
So, exploitation here means eventually you have to use what you know. So, let's say we had a blue and a red machine. You started playing only with red, okay? And let's say you are always getting $2, $2, $2, and you don't really know what blue does. So if you are, let's say, 10 chance mein you always played on red machine, okay? You always got $2, let's say. Now, in the 11th time, if you again go and press red button, that would be exploitation. So you are just using what you know. What would be exploration? You go and try out something that you have not tried out until now. So if you start, so you have to try unknown actions to get information. Why is this important? So let's say you have, getting all the time 2 from red machine, that's one of the best cases, right? You can't really do better from the setting that we know. Now, let's say you go and push the blue machine. It gives you $1. What should I do next? Play red. So now let's say from 12th time onwards, I start getting 0, 0, 0. What will you do in 4th time? Maybe try blue again, because that guy was at least giving me 1. Ideally, after infinite such plays, will you get to know the exact probabilities? So let's say if you play blue 1000 times and you have always got $1, what is a reasonable thing to expect from there now? That blue gives me $1 with probability 1. And similarly, if 1000 plays on red machine gives you 750 times $2 and 250 times 0. What's a reasonable thing to assume? That the probability of getting a 2 from red is 0.75, and so on. If you do this infinitely many times, then you get the exact probabilities. But doing something infinitely many times, is that a good idea? You will eventually learn the perfect thing, but the problem there is nobody has infinite time, right? So the purpose of machine learning that we do is not to learn the correct model in a infinite time. The purpose is to learn the useful model in a given time, right? So you may not have the perfect thing, but something that's reasonably good.
The
That's what reinforcement learning is.
If I did 100 times,
हाँ,
तो मेरे को learn होता है कि okay, blue is given this, red is given this.
right.
But then फिर मैं blue करते रहा. Eventually मैं कर रहा हूँ, I'm not like learning it, कर रहा हूँ.
So
At that time also I'm learning कि वो हो रहा है, probabilities at the same time compute होते जा रही है.
so how is that different from what I just said?
नहीं मतलब maybe मैंने learn कर लिया कि blue का दे दिया, red का दे दिया in 100 times, so मैं 100 times कह रहा हूँ, मुझे learn हो गया.
Okay.
उसके बाद मुझे actually after that my actual game starts.
Okay, now what?
In that time also I'm learning और फिर I just perform कि वो एक point से समझ जाएगा. फिर उस time में मैं learn करूँगा.
I'm not sure I get this.
पहले हमने लर्न कर लिया 100 टाइम, अब हम जब भी कर रहे हैं उसको लर्न नहीं कर रहे.
नहीं, but can you learn in this way? Can you learn in any time less than infinite time? Because who knows? So will the, in real life if you go, will the probability of $1 from blue machine, is that always blue? Sorry, is it always 1? Can you give me examples in which case this will break? Let's say machine has run out of the coins. So in that case, even if you push the lever, you won't get a $1. So in that case you will 0. So even blue can give you 0. थोड़ा सा मॉडल तो एक्सपेंड कर लो, right? So in that case, let's say you pull this lever 100 times, you get $1, but 101th time you got a 0. Is the probability of getting a $1 from blue equal to 1 anymore? No, it is 100 by 101. So it's something less than 1. So
नहीं अगर ऐसा ऐसा एक hypothetical situation में है कि blue I'm playing red, I have done 1000 times, and blue हमेशा मेरे को initially 0 देता है. For 1000 time I got 0.
okay,
For blue I got 1.
okay.
But suddenly my red machine started giving me $2 every time.
Suddenly कैसे? After 1001? Okay.
I started getting $2. But अभी तक मैंने learn किया है कि red is giving me 1, blue is giving me 0. So I'll still play red or I'll switch to blue. मतलब उल्टा I switch to red or I'll still play blue.
See, that is up to you. But the point here is, if after 1000 zeros, red starts giving you $2, है ना? So maybe you are in a super bad case. And can you say your learning is over? No. You have not converged to the probabilities. Let assuming probability was 0.75, right? अब बहुत ही गंदे केस में हो, because एक साथ 1000 जीरो आने की probability, given that the probability of 0 was just 0.25, this is very low. 0.25 to the power 1000, right? So these two are very important concept. Okay, and we'll see a lot of them in the next lectures. All right, so we start with RL now. So reinforcement learning, you will see this diagram everywhere wherever you see an introductory thing on RL. So you have an environment, you have an agent takes action A, right? Once agent has taken action A, now agent has no control, right? Environment will decide and will give some, will throw out some reward R to agent, and then agent will go to some state S. ये अपन अभी तक करते हैं. So agent takes an action A, environment responds, agent ends up being in some other state or maybe even the same state, reward R. Okay, ये चीजें अपन कर चुके हैं MDPs में भी. Basic idea is to receive feedback in the form of rewards. Agent's utility is defined by the reward function, must learn to act as to maximize expected rewards. Nothing new here. All learning is based on observed samples of outcomes. This one is new. So receive feedback in form of rewards. This is what we saw in MDPs too. Agent's utility is defined by the reward function. Again we had seen it. And then must act so as to maximize expected rewards. Now all learning until now we were looking at how to solve MDPs. We were not talking about any sort of learning out there. So all learning is based on observed samples of outcomes. So I think it is much better to show their videos now. At least these things should be seen.
What the models are for the learning for. Okay, so people apply this with robot dogs also. So this is some results I'm going to showcase from Peter Stone's group at the University of Texas, Austin. And there's something called RoboCup. In RoboCup, robots play World Cup soccer among each other. And one of the leagues is the dog league. This is the dog league robots. These are Sony Ivo robots, which just came back into production. And now, if you want to do well in soccer, it's actually important to run fast. It's hard to beat them. And so one of the things that they use reinforcement learning for is to train their robot dogs to run as fast as possible. So you can imagine you run reinforcement learning in the lab, and these dogs learn how to run. But then you put them on the actual field, and the field is a little different from your lab field. And they might not do as well, because there's different friction, different properties of the terrain. So what now? Or maybe the dog has played a lot, and a little bit of wear and tear makes it different than how it behaved in the lab. Then what you want to do, and what they did is they say, well, we have an initial thing. Before we play a game, we can run our lab-trained control policy. It's okay. In the lab, it worked really, really well. But out here, on the actual scene of the World Cup for robot dogs, it is kind of slow. Then they say, let's rerun a bunch of trials and run reinforcement learning in the background, and we'll understand better what that means. But this is what it would do before a game starts. It just starts running on that terrain and practicing, understanding how that terrain interacts with its legs. And then after full training, before the game, here's what you get, and you get maximum speed and also very stable head to see what's around you, locomotion. These dogs beat pretty much every other team all the time. Here's another example of a result obtained with reinforcement learning. What we have here is a snake robot. How to build a snake robot? Essentially just a bunch of motors sequenced together, and that allows you to build a snake. So if a bunch of motors sequenced together here, the training has already happened. So it's been trained to control itself, to climb on top of the step and sideline. Let's see how it does. This is a project in Andrew Ng's lab at Stanford about maybe 10 years ago now. At the time I was still there. And you see, indeed, the snake is able to get onto that step and actually wants to get to the other side. So once it's on, it'll start sidelining and make its way over. And you might start seeing a pattern here. And the pattern is that for solving these problems, it's very difficult to build reliable simulators. So far in 188, we've looked at scenarios where we can have a model, either the deterministic or stochastic model of how the world works, and we've been planning it. But for things like this, how do you build a reliable snake simulator? It's very hard to do. Not clear if anybody can do this at this point in time that would match this particular snake. And so if you build a simulator and it's not good, well, then whatever you plan in that simulator might not be a good plan for the real snake, and it might not work in the real world. And so that's why reinforcement, when it comes to the rescue here, you can let the thing learn on its own, on the task it's supposed to do well. Here's another example. This is from Russ Tedrick's PhD thesis at MIT. So what are we looking at here? This is a toddler robot. Making a two-legged robot walk is actually pretty tricky, because if you only have two legs, by default you're going to fall over. And then once you fall over, it's hard to get up, especially this robot design wouldn't know how to get up once it's fallen over. And also you might damage the robot. So Russ kind of used some cleverness on both the design side of the robot and the reinforcement learning side. On the design side, if you look at this robot, actually, and hard to see from here, but the feet are curved. And so what it's naturally really good at is going like this. And if you know how to go like this, then you have lifted a leg at any given time, you can swing it forward, take a step, and repeat. And it turns out if you put this robot, I believe it's roughly 8 degrees downhill slope, and you start it off to the side so it's wobbling, because of gravity, the downhill slope, it'll swing a leg forward when it's off the ground, and it'll actually gradually walk down that 8 degrees or 50 degree slope that it's designed for. So Russ designed it to passively walk down hills without any control needed if the hill has the right slope. So that means your design is in the right space that it in principle should work. If you now kick a little bit of energy into it, maybe it can walk on flat surfaces too. And that's exactly what the reinforcement learning took care of. So initially, when the reinforcement learning starts, it doesn't know how to control the system. And it's just kind of wobbling back and forth. That's what happens when you just randomly put energy into the system. It'll start wobbling left, right. But it gets rewarded for making forward progress. And so over time, you start figuring out how to make some forward progress. Right now, it's kind of just circling around on exactly straight line forward progress. But over time, it becomes better and better, making this kind of consistent progress. And after a good amount of training, it just walks off, it's gone. In your project 3, you'll get to do something very similar for this robot here. So this is sometimes the simplest locomotion robot you can imagine. You might wonder, why do we keep it so simple? Why don't we have like a full humanoid robot? Wouldn't that be awesome? The running time for reinforcement, the amount of experience it needs to collect to control a full humanoid will be much higher than for a lower dimensional robot. And then it would take maybe a day or so to run your project code. And then if you had a bug and it didn't work, you'd have to go again. You'd only have a few trials before deadline is hit. Whereas this one, you can run relatively quickly. If it doesn't work right, you can debug it and repeat. So how do you make this thing move? Well, you can control two angles. There is an angle over here and an angle over here. That's where your motors are. You can control those angles. And if you're smart about how you do it, this thing can move. So let's take a look at the video of this in action. This is the robot kind of just, oops, let's mute this a little bit. So what are we watching here? The robot is just randomly moving its arm around, and sometimes it means it moves forward, sometimes it means it moves backward. But we give it reward negatives for moving backwards, positives for moving forward. And the hope is that reinforcement learning, based on that signal, can figure out what is a good policy to control the robot. Now this takes a while, so in this video that we're recording here, we'll skip forward a lot of attempts, so we're not watching all the learning in action. You might wonder, why is this hard? Why isn't it easy to just pedal yourself forward? Well, it has a lot of options in terms of what to do. And it doesn't know ahead of time how it works, and has to figure it out from its own experience. And in fact, when you reach forward, you don't move. It's only once you put your pickle down and start pulling you move forward. So first you need to go through a phase where nothing happens for you. You don't get rewarded. And so it's hard to learn to do that because you don't get any signal that's the right thing to do. That's like giving your dog no feedback for a whole day, let's say, and then at the end of the day say, good dog, that was a great day today, or bad dog. It's not going to learn. The more your reward is spaced out over time, the harder to learn. And so what makes this hard is that you do need that period of getting no reward and somehow discover that that's the way to achieve reward in the long run. So if you successfully complete your project 3, you will have implemented a reinforcement learning algorithm that learns to control the crawler bot. Okay, let's formalize a little bit what we're thinking about today. Reinforcement learning. We'll still assume that we're working with a market decision process, which we've looked.
Okay, so I mean, go and have a look at these lectures anyway. All right, so right. So this is what we had as an MDP. Now if we want to say it's not MDP, let's say we want to kind of quote in quote convert it to reinforcement learning, what should we do? Right? So basically all we are saying is, if you don't have the complete information to solve an MDP, right, then that becomes, that requires you to learn something, and that kind of learning is what we call reinforcement learning. So here in this case what they do is, so again it's still an MDP, so state, a set of states, set of actions, model T, reward function R, and still looking for policy pi s. This is, so we are still doing everything same as we were doing before. The only difference is that now we don't have some information that we had while solving MDPs. New twist, we don't know T and or R. So either T or R or both. So we don't know which states are good for or what actions to do. Must actually try out actions and states to learn. Okay. All right. So what is offline MDP versus online RL? Right. So offline everything is given to us. We can just go and solve the MDP, right? So thinking, planning, and then look for the optimal value, right? In online learning, you are here, you don't really know there is a fire pit out there. You have to go experience there is a fire pit out there, and then you experience negative rewards, and that's how you start learning about the space that you are in. Model based learning. So model based idea, learn an appropriate model based on experiences, solve for values as if learned model was correct. ये जो अपन अभी गेम वाली चीज में कर रहे थे, when we were trying to extract probabilities, so let's say you do it for 100 times. So let's say you play red for 100 times, you play blue for 100 times. Okay, blue let's say gives you 100 times $1, and let's say red one gives you 60 times $2 but 40 times 0. What is the model that you have learned? the probability of getting $1 from blue is 1, but the probability of getting 2 from red is 0.6 and 0 is 0.4. But let's say somebody who has designed it knows it that the probability of getting a 2 is actually 0.75. So you can learn an approximate model based on experiences. Okay? If you want to learn the exact model, how many times should I experience? Infinite. Okay? Solve for values as if the learned model were correct. So now, since we don't know, nobody tells us that it was 0.75. So how will we solve after these 200 experiences? So 200 experiences we did, 1 cross 100, 60 cross, 2 cross 60 and 0 cross 40. So we assume that the probability of 2 is 0.6. Okay. Solve for values as if the model that we have learnt is correct. So this is one way. अब देखो इसमें इतने सारे नाम आएंगे. Whatever we had done before in MDPs, we had a lot of nomenclature. All were talking about Bellman updates, but then they were, so all were dependent on Bellman equations, but they still had different names and different way of doing things. Here you will do exact same thing, but different names under the hood of RL. Solve for values. So right now we are talking about model based learning. What might this model based learning mean? I just talked about it, right? So you did it for 200 experiences, built a model out of it, and then finally solved the MDP. Step 1 is to learn empirical MDP model. Count outcomes S prime for each SA. So this is what essentially we just talked about. Normalize to give an estimate of T. This is what we just said, ki probability of this is 0.6, 0.4, 1. Discover reward when experience SA to S prime transition. Now solve the MDP that you have just learnt. For example, use value iteration as before. Right. Exploration, exploitation you always do, but उसको formally आगे करेंगे. कौन सा वाला? Discover. So we said R is not known, right? Discover each reward. So you pulled, if you are pulling the lever from blue machine, you are always getting $1. That is the reward. So you are discovering that reward is 1. Okay. If you are doing it for red one, you can get 0 or 2. Okay. So once you have figured out what is R, what is T, now you can go and solve the MDP. Okay. This is one way of doing RL. That's what we just have.
But 200 is not sufficient.
So then do it 1000 times.
That is also not sufficient.
So that's what we are saying. See, if you want to do learning, you have to have a trade-off, because if you think you want an exact model, that will take you infinite experiences, right? So either you go and build a perfect model, or you go and build something that is reasonable and solve that. There is a trade-off. So if you think 0.6 probability, so actual is 0.75, you get 0.6. If you think this is not sufficient, maybe go and do more experiences.
Normalization is finding out the
So whatever you have, these probabilities is what we mean by normalizing. Okay. So model based learning. So we are given this particular input policy, okay, observed episodes, these are the trainings, and we are supposed to come up with T and R. Okay, and we are supposed to find T and R. How do we do that? एक बार have a look at this particular thing. ये same अपने grid वाली चीज से है. So for example, this one training episode, you start from B. From B you go east, C. How much reward do you get? -1. You are experiencing this. They were not given to you. Okay. From C you take action east, go to D, and you get reward -1. Okay. From D you take exit, and then you get reward +10. So this was just one episode of training. What happens in episode 2? What happens in episode 2? You start from B. So same as this one, right? So you start from B, take action east, go to state C, get reward -1. C east D -1, same as this. D exit to whatever state, and then +10. These two are same. What happens in this case now? You are in E, take action north, go to state C and get reward -1. You are in C, take action east, go to D -1. D से exit +10. E north C -1. C east A -1. So C east, last time it was D. Now C you took action east and you actually go to A, take exit and get reward -10. I want you to help me figure out what is the reward. So reward is given to you. So what are these transition things? No. So what are the probabilities? So let me just give this to you. Okay, and then tell me how did we arrive here. So T, remember this was SA S prime. So T of SA S prime is 1. Why so? See, look for in your training episode how many instances do you have for B is C. B is C. Anywhere else? No? So I have 2 instances. In both of them, when I was in B, took action east, went to C. So the probability of going from B to C is 1 if I take action east. Okay? But even if it is noisy, can this happen? It can still happen. But आपके training episode कितने हैं? Just 4. So you can just look at these 4 things and try to construct the model. Okay? What happens with this guy now? So पहले देखो C east D के कितने instances हैं? C east D, C east, right. So now we'll talk about this one. right? So why do we have 0.75 there, 0.25 here?
Because the current would have been
See,
very much bigger.
right, so from state C, 4 times you took action east, 3 of the times I went to D, so 0.75, once I went to this, so 0.25, keep on doing this for all the transitions that you can think of, okay? And similarly for rewards. मॉडल बेस्ड लर्निंग, अगेन देखो मॉडल बेस्ड आएगा, मॉडल फ्री आएगा, फिर उसमें भी बहुत सारे आएंगे. सो व्हाट इज मॉडल बेस्ड? You are given a particular policy. Observed episode means training, train your model, learn the values of T and R. This is all we are doing. Once you have the values of T and R, what can you do? Solve MDPs. Okay? Yes. What is?
If we go from B is to C minus 1 और ये episode 1
कौन से वाले में? एपिसोड 1 में? हाँ.
B is to C minus 1
हाँ.
that minus 1 is showing that A is where
You observe -1 reward.
if we are taking action there then the reward will be minus 1.
If you are not you can't take exit here. This is not an exit state. So this is your living reward, whatever we were calling it before. So if you go from B to C, sorry, transition. So if you take transition from B to C, taking action is, that is your yes.
So for getting B to C we are getting minus 1.
Sorry. So see, this is simply this part. You are in S, take action A, go to S prime, get reward R.
This is not living reward.
Living reward is what?
This is just transitioning reward.
So that in a way is living reward, right? Is this fine? Now if you go and experience more, so maybe these probabilities will also change, okay? So something that you have assigned 1, just because you have seen only 2 instances, or वहाँ पे this is the only thing you could see. So that's it. देखो, how can I compute expected age of whatever population? जल्दी से करते हैं इसको. राइट, एक बार हिंट दे देते हैं, देन see what happens in this tree, what happens in this part. The claim here is you are computing expected age using this and you are computing expected age using this. What is the difference between these two?
For particular action
See, okay, let me elaborate more here. Here it is saying, so this part you do without having the probabilities, okay? See, goal is to compute the expected age of something. What is this formula giving me? How do we compute expected values? बिना देखे, एक बार देख लोगे तो गड़बड़ हो जाएगी. बिना देखे सोचो. You've done random variables before? Yes. So how do we compute expected values? Acha, if I give you a dice that has 6 faces, what is the expected value? No, I'm not asking you probability of a face. I'm asking you what is the, so a dice has numbers from 1 to 6. What is the expected value of, one throw? That this is what I will get. Expected value is a number.
weighted average दे दो ना उसका.
हाँ तो बताओ ना.
weighted average.
What is that?
1/62 number.
Right. So 1/6 into 1 plus 1/6 into 2 and so on. So it is basically 1/6 into summation 1 to 6. So summation 1 to 6 is 21, that gives you 21/6, 3.5. Okay. So this is, what is this? Probability of A multiplied by how many instances of A. Do it sum over all A's, what you get is expected value. Here, just 1 minute, है ना? Here, सुनना बंद कर दिया है. Okay. So here, let's say out of your whatever, let's say 800 students, you randomly ask 50% their height, right? And just take average over that. Why are these two things the same? एक में you are explicitly given these quantities. In this case, since you are drawing from this sample, right? So most likely you are drawing it from the distribution that this particular thing already follows. So let's say there are 800 students or whatever number of students. Okay. If age की बात हो रही है, so let's say what is the probability of drawing a person who has age 60? Very low, let's say. Okay. What is the probability of drawing a person who has age 10? This might be 0, right? So ज़्यादा, so let's say if out of 800, 400 are 20, 200, so let me make things simple, and so let me just make things simple, let's not distribute it further, 90. Okay. So if you are randomly selecting students, so if I randomly select 80 students, what do you expect? Of these 80, how many will belong to which group?
Half to 20. Half to 20.
So half this side, so 40 will come from here, 20 from here, 20 from here, right? So that means when you are randomly picking up your population, this already follows the distribution. So you don't really need to multiply probabilities here again. Maybe this was not the best slide to conclude, so we'll start from here in the next class. Attendance?
Sir, next semester is wonderful. Next semester, deep learning है फिर ये वाला तो पढ़ना है, तो मर्डर करेंगे.
Yes. I wanted to take LLM next sem, but उसके लिए मेरे को इस sem deep learning करना चाहिए. Exactly, and I was not allowed to teach deep learning to 5th sem because 5th sem should do AI, so it should be. नहीं but
हिंदी भी तो एमए से AI के बाद ही करेंगे. वर्किंग में AI के बाद हमें थोड़ा.
देखो it does not matter. मतलब even